Hello and welcome back to another episode of Dome to Home, guys. My name is Jeremy. It's so nice to be back here after taking last week off. Had some much needed rest, but I'm super excited to be back and learning about water in the solar system. With me, as always, we have Tara. Hey, Tara.
Hey, Jeremy. Hi, everybody. So good to see you again this week. Again, I'm Tara. I'm a planetary scientist and a CU alum and love hosting Dome to Home here with all of our buddies. Of course, we also have Raimi in the background as our question master. She's back there monitoring the chat. So if you have any questions that pop up, go ahead and drop those into the chat box. You can also use a new thing that we have for questions. We have a form. There should be a link in the chat or also in the description of the episode. So if you have trouble using the chat feature in YouTube, you can use that form link, submit your question that way. We'll try to answer some questions as we go along, but we've got time dedicated at the end for questions too. And of course, remember, if at any point you have trouble seeing some of the things that are happening on the screen, make sure you're doing your YouTube video in full screen. It'll make it nice and big. You can see those stars and all of the other cool things we're going to be talking about today. It's like Jeremy said, we are here talking about water in the solar system. That's our theme for all of this month. So each week in March, we're going to be bringing you something new and different about water in the solar system, like Jeremy's got there. It's a little bit of water in our solar system.
Water in my house, which is in our solar system.
I've got some water here in the solar system as well. But I want to ask all of our viewers out there, do you know how much water there is in the solar system? Or specifically, how many planets do you think have water on them? Now, of course, here we're looking down at our Earth. You can see Earth obviously has tons of water. You drink it every day, hopefully. You've probably seen water quite often. There's probably some frozen water out in your yard right now if you're still in Colorado like we are. But how many other planets have some form of water on them? Jeremy, why don't you show us which of our planets here have water?
I'll bring up all the orbits of the planets that have water for us. So we see the blue line is the Earth there, and you might notice that there is, 7 other lines that have appeared here?
8 altogether. Did any of you guess all of the planets? Because it's true, all of the planets have some form of water on them. Not necessarily liquid water, although a lot of them do, but it also could be ice or water vapor. Now, planets are not the only places that we find water or ice or water vapor in our solar system. We can count most of the moons too, but there's also water in places like the asteroid belt. We see tons of water out there. Most of our dwarf planets have water on them as well, or at least water ice or water vapor sometimes. So we can include those in our calculations too. We also find water ice on comets. In fact, most comets are made of ice. And so there's tons of water ice floating around out there in the form of comets. Some of them are what we call short period comets. They stay close to the sun. Long period comets go far out from the sun. Look at that, crazy. And that's not even all, because we also have water ice found in things called the Kuiper Belt objects, out in the Kuiper Belt, out at the very edges of our solar system. So those are all of the places just in our solar system that we find some form of water. So a lot of times you ask people where there's water in the solar system, and they think of, oh, it's very rare, maybe just Earth or maybe 1 or 2 other places. But water in our solar system is actually everywhere. It's all over the place. Now, this probably shouldn't be too surprising if we stop to think about it, because water we know is made from hydrogen and oxygen, H2O. Well, hydrogen and oxygen are 2 of the most abundant elements in all of the universe. Did you know that part? Now, this is because both of these elements are very commonly made inside of stars, even stars like our sun. So we're going to zoom in and take a little bit of a closer look at our sun, and we can think about our sun and other stars and how they work. Well, what are stars doing? They're basically putting out all of this energy because they're constantly undergoing nuclear fusion. Big, scary words. But basically, they're always just smashing atoms together to make bigger atoms. So we start with the simplest one, hydrogen. It's just one little proton and one electron. You could smush two of those together and you get a helium atom. You smush two heliums together, you get something bigger, and they keep doing this and keep doing this. So there's tons and tons of hydrogen there because that's the main thing that stars are made out of, but they're also fusing these other bigger elements. Now, medium-sized stars like our sun, small, medium-ish, are gonna fuse elements up to carbon, which is number 6. So there's still a lot of hydrogen, but it only goes up to carbon. But bigger stars will fuse bigger elements, including oxygen, which is number 8. So big stars will fuse all the way up to that and beyond. There's a great picture of our sun. You can see it's really active. There's lots of different regions. There's bright colors and darker colors. There's always stuff exploding. Stars are really cool. So, speaking of exploding, when a really big star dies, you may have remembered from some of our other videos that they kind of explode and make something called a supernova. And so all of those elements, the hydrogen and the oxygen and everything else that was inside or around the star, gets blown off into space and makes these huge clouds that we call nebula. And we can show you our picture that we always like to show of the Crab Nebula, which is everybody's favorite nebula. Look at that. That's so pretty.
Can't go wrong with that.
I know, right? Well, we can look at this a different way too, and look at just the hydrogen and oxygen in the Crab Nebula. This is a great picture that we have thanks to the Herschel Space Telescope and the Hubble Space Telescope. So they took this picture in different filters. Now the red areas are where there's hydrogen, and blue areas is where there's oxygen. So we're just seeing those two elements. You can see there's a lot of overlap. There's a lot of purple in there. So that may or may not be actually combined into water, or they may just be really close together. But you can see in these clouds, there's tons of hydrogen and tons of oxygen. Now, the important thing about these clouds is that's what other stars and eventually planets and asteroids and comets and all of that stuff, this is what they're made out of. So all of that hydrogen and oxygen could combine into water, and it could be incorporated into all of the other things that are forming from these clouds. Now, we're going to talk a whole 30 minutes next week about where water comes from in our solar system. So we'll get really deep into that with Miss Rainey next week. So definitely come back to check that out. We'll talk a little bit more about where this water all comes from. Now, if you were with us last month when we spent all this time talking about exoplanets, you may be thinking, well, there's water everywhere. What about this Goldilocks zone thing that we always talk about with the exoplanets? What's that all about? Well, Goldilocks zone is still a thing, and it's still an important thing. Now, basically what the Goldilocks zone tells us is that, at a certain distance from a star, you're going to have conditions that are favorable for life. And a lot of times when we think about life, we think about liquid water specifically. And that's just one consideration. If you look at the picture here, this is our famous Goldilocks zone in our solar system, so around our star. You can see that Earth, yes, is firmly right in the center of the green zone, the good one. And so we've got lots of liquid water. It's a great place to be alive. You can see that Mars is kind of out towards the edges where it's a little bit cooler. And we don't see liquid water on the surface of Mars. We do see a lot of ice, though. So there is water in the form of ice. On the other hand, if we look to the other side, Venus is right on the edge of it being too hot. And so we don't see liquid water on the surface of Venus either. But we do see water vapor in its atmosphere. It's still just very little, but it's there. And so that tells us a bit more about how water is important based on temperature. So we do see that where it's colder, there's usually a lot of ice. Where it's warmer, it's usually mostly vapor. And right in the middle is where we get the good liquid stuff. So temperature does play a really important role in where we find different kinds of water. But there's other things too. Pressure is another big important thing that determines what kind of water, whether it's liquid or solid or vapor. Now, scientists have something that we like to call phase diagrams or PT diagrams or temperature pressure diagrams. They've got lots of different names. And this is kind of what one would look like for water. Now, you don't have to memorize this. This is just to kind of give you an idea of how we look at it as scientists. You can see where there's really low temperature and really low pressure. You're going to see mostly ice, but maybe also some water vapor there. Really high temperatures and high pressures, you're mostly going to find water vapor, but you also get close to liquid water, depending on where the pressure is. So that's another thing that we have to consider when we're thinking about where we're going to find different kinds of water. Not only how hot is it or how cold is it, but what's the pressure like on the surface? It's kind of a weird thing to think about. But that definitely means that there are places where we find things like ice and water vapor and even liquid water that you wouldn't necessarily expect just based on how hot it is there. I think a great example is that we find ice on Mercury, of all places. On the poles of Mercury, the planet that is closest to the sun, it's the second hottest place in the whole solar system, next to Venus, but it's got ice in these craters near the North Pole, which I think is crazy. And that's partly just because that these craters are deep enough and they're at enough of a high angle on the planet that there's areas that actually never get any sunlight. And so it stays very, very cold at the bottom of these craters. And so ice is able to form. This is the same thing that we see on the South and North Poles on the moon. And we're going to talk more about the moon and ice and water in 2 weeks too. So definitely come back and check that out with us. Now, aside from just temperature and pressure, there's other things that can contribute to us finding different kinds of water places. Now, a lot of you, if you read even the description for this episode, you probably know that there is liquid water on some of the moons of Jupiter or moons of Saturn. We find water, liquid water, really far out into the solar system. It's pretty crazy. Now, this can be for a couple different reasons. And one of the really important reasons, at least for the moons of Jupiter and Saturn, is this thing we call tidal heating. We can give you kind of a demonstration of how this works. To do that, we're going to head over to Jupiter. Jeremy's going to fly us over there.
Flying in the background. We already maneuvered our way over there. So here we are looking from the top down at Jupiter there with Io, Europa, Ganymede, and Callisto. I had to say those in the right order. The 𝐀𝐭𝐢𝐗𝐬 planets are moons around the giant planet of Jupiter.
Yeah, so those are the 4 biggest moons around Jupiter. We call them the Galilean moons because they were discovered by Galileo in the 1600s, forever ago. So what's really important about these moons, they're a great example of this tidal heating thing. And basically how that works, we see Jupiter's there in the center. Jupiter is huge. We know it's the biggest planet in the whole solar system. You could fit 30 Earths inside of Jupiter, et cetera, et cetera. Now, we've made the little moons a lot bigger here, too. They're actually much, much smaller in comparison to Jupiter. You wouldn't be able to see them, though, so we've embiggened them a little bit for you. So as these moons are orbiting around Jupiter, they're not orbiting in a perfect circle. It's more of an ellipse. It's sort of stretched out. It's hard to see on the screen. But at some points, they're closer to Jupiter, and some points they're farther away. And so as they're going around, they're getting pulled by Jupiter's gravity, sometimes a little more in places and a little less when they're farther away. But you can see there's also the other moons that are going around. And these moons are in a special, what we call resonance, which means that Io, the innermost moon, for every time Io goes around, every time Europa, the second moon, goes around once, Io, the innermost, goes around twice. And if we go one farther out, Ganymede, the third one, every time it goes around once, Io goes around 4 times. So they're in this pattern to where they line up at certain points in time. And so sometimes these moons are getting pulled by not just Jupiter's gravity, but all the other moons too. And they're getting pulled in all different directions. And so that means the insides of these little moons is getting like squished and stretched and squished and stretched. And all of the squishing and stretching causes it to build up a lot of friction and a lot of heat. So if we look in particular at that second moon, Europa, It's mostly made of ice. It's almost ice. It's all the way around. The outside is ice, but underneath all that ice is a ton of water. Because this tidal heating from the very center of the moon is causing enough heat to where we can melt a lot of that ice and have this huge liquid water ocean underneath. And just like we said on the description earlier, it's more water than on the entire Earth combined. And Europa's smaller than our moon. So that's a lot of water. Now, these subsurface oceans, we call them, are actually popular on lots of the moons around Jupiter and around Saturn. Ganymede, that third moon out, has a subsurface ocean too. Some of the moons around Saturn, maybe you've heard of Enceladus is one of them. Lots of those moons, even moons around Uranus and Neptune, they all have this tidal heating process that we think contributes to them having oceans under their surface, which is pretty sweet. Now, if we go even farther out into the very farther parts of the solar system, we see things that are liquid, but not necessarily water sometimes. Like there's one, you may have heard of a Saturn moon called Titan. It's a really big moon, goes around Saturn. It has lots of liquid on its surface, but it's not liquid water. There's lots of water ice on the surface, but all of the liquid's actually made of methane. And again, this comes back to that pressure temperature thing. Methane here on Earth is all gas, but when you get out to where it's really, really, really cold and sometimes high pressures, you can get liquid methane. So look at all of those oceans, those lakes that you see in this picture here on the surface of Titan. They're all liquid methane. It's probably a very, very stinky place to go water skiing. I would not recommend.
Wouldn't probably want to go for a swim on those beaches.
Not so much, no. No, it's like swimming in a big fart. But we can go even farther when we get out to the very edges of the solar system. Maybe someplace like everybody's favorite dwarf planet, Pluto. Pluto is very, very, very far from the sun. And yet, Pluto might not be another example of one of those places that has a subsurface ocean. We're not 100% sure yet. We're still analyzing all of this great data that came back from the New Horizons spacecraft that flew past Pluto in 2015. But we've got really great pictures of all this weird stuff that's happening on the surface. And by looking at what's happening on the surface of Pluto, we can get an idea of what's happening underneath Pluto too. And so we think now Pluto might also have a ton of liquid water underneath the surface. Now, of course, on the surface, there's tons of water ice, and it's so hard that it's like rock, and it makes huge water ice mountains, which is pretty neat. But then underneath the surface, there's all of this liquid water. Kind of makes like a ring around the center, which is pretty cool. I think we have a cool drawing done by a guy named James Keane, who's a planetary scientist. He does lots of really pretty illustrations of things. And this is one that he did for Pluto. He's on the New Horizons mission. And so he's got really great data to work with. You can see how there's all the icy stuff on the outside and then that thick layer of water underneath. So these are the things that we have to think about. You wouldn't maybe think that there would be liquid water somewhere like Pluto, so far from the sun and so far out there, and it's so cold. But under the right circumstances, we can find liquid water all over the place, which is really exciting. And that's why we have a whole month's worth of stuff to bring you guys about water in our solar system, because there's so much of it and there's so much for us to talk about. And that puts us right at our 20-minute mark. So now we definitely have time saved for questions. If anybody had any questions that came up about water in the solar system, how we get it, what's different about water, ice, vapor, I'm happy to answer any of those. Water and ice in the solar system is one of my specialties. It's one of the things that I do for my research. So I'm super excited to talk about it all the time. I will always talk about it.
Yeah, bring on the questions.
Yeah.
Ready to go with the water questions. Looks like Era Sprite wants to meet some space mermaids.
That would be cool.
That would be pretty cool. Yeah, finding some sort of new type of life, like even just mermaids or even just any type of space life somewhere else would be very interesting to meet.
Yep. It would. And these places that have these subsurface oceans like Europa and Enceladus and some of these other moons, those are some of the best places for us to look for life. At least life as we know it, needs liquid water to survive. Pretty much every part of your body needs water. If you don't drink water, you die. And so a lot of animals here on Earth are like that. And so that's one of the things that we look for when we're talking about where we might find life. Planets with liquid water or moons or asteroids or whatever. Those are always great places to look. Ooh, a question from our Google form. What is my research with ice in the solar system? Well, I have a couple different things that I do. One of those things is looking at craters on Europa, that planet around Jupiter, or the moon around Jupiter, the second one out that's covered in thick ice on the outside and all the liquid water underneath. I look at different parts of those craters to see if maybe there's a point where a big meteor has maybe broken through the ice and water has come up from underneath it. We can get an idea of kind of what's inside that water. That'd be super cool. So that's one thing. I'm also currently working on a project that's mapping ice deposits in those craters on the south pole of the moon. So that's for the brand new Artemis program. We're going to talk a lot more about these missions to find water in the solar system. Week after next, I've got a whole segment based on just missions that are looking for water. So those are the couple of things that I do. What else do we have? While we're sitting here looking at Pluto, one of the cool things that I think about Pluto is that what we would normally have here on Earth, like glaciers and big ice deposits that would be water ice, on Pluto, there's a lot of the same landforms like glaciers, but they're all made of nitrogen ice, which we don't even have here on Earth. The best we can do is get like liquid nitrogen. That's like what they use to freeze things really quickly, like Dippin' Dots. That makes things really cold, really fast. So even liquid nitrogen is super, super cold. But out on Pluto, it's so cold that it gets frozen on the outside. And so there's glaciers made of nitrogen. The heart-shaped region on Pluto, called Sputnik Planitia, is all made of like this nitrogen ice, but it's kind of slushy. So it actually kind of what we call convex. It sort of boils, but like a cold slushy that makes these little cells. It's really neat. I think it's super cool.
Yeah, the science that it still is coming back from New Horizons mission is really changing our ideas of what or how we kind of thought about water in our solar system and what we expected, the cutoff to be able to see things like mountains built of water ice all the way out at Pluto. So definitely a very, very cool mission that I'm sure a lot of new discoveries are going to continue to come from.
For sure. Yeah. Like I said, it flew past Pluto in 2015, and we're still making new discoveries in that data 6 years later. It's pretty exciting. Great question here. How many different kinds of ice are there? Depends on what you mean. So if you're talking about ice other than water ice, things like that nitrogen ice or carbon dioxide ice, there's all kinds. Pretty much any element you could think of that has a liquid phase would also have a frozen phase if you got it cold enough or under the right conditions, like that temperature pressure thing. Pretty much every element has a diagram like this that people have scienced out. They've done a lot of experiments to see what happens when you put different materials under different pressures and temperatures. So lots of elements go through this process, and we can make them into ices. Now, here on Earth, it can be really difficult because our conditions are very limited, and there's only so much pressure and so much temperature that we can manipulate safely here on our planet. But other places, we see those things like methane ice, nitrogen ice, you name it. It's all over. Now, if you're talking more about how many kinds of water ice there are, that's a thing too. Now, there's what we call different high pressure phases is kind of how we refer to them. But basically, if you take water and put it under enough pressure, it will go straight into that ice phase, no matter how hot it is. And there's different sort of divisions. If you put under this much pressure, it makes something called ice 1. Ice 1 is what we have here on Earth. So at Earth temperatures and pressures, we make ice 1. But you can go places where you can put more pressure under that ice, and it can form something called ice 2, which is still made of water. It just has a different structure to the way that the atoms are arranged. And if you keep adding pressure, it changes that structure into these different phases of ice. We have ice 3, ice 4. These are not naturally occurring things. It's been hypothesized that you could have ices all the way up to 18. In fact, that's what they think is maybe inside planets like Neptune and Uranus. They're so big and there's so much pressure at the center that there could just be these really high pressure forms of ice, which is really cool to think about. I think these are the things that I get excited about. Ice 18, what even is that? That's a great question. There's tons of different kinds of ice. Here's another one from Ari Sprite. The moons that have entirely water, do they have a molten rock core as far as we can tell? Like if the Earth was just oceans, or is it more a ball of water like the gas giants? That is an excellent question. Now, we don't know for sure because we've never been able to land on one and go down to the bottom of it. But based on different things like gravity and density measurements and some of the other measurements we've been able to do with spacecraft, we think that moons like Europa and Enceladus probably don't have a molten core, but there probably is a rocky core at the center. So it may not be liquidy magma like we have on Earth. It might be all the way solid through, but we're pretty sure that there is something rocky at the center of those, as far as we know.
I think also, isn't it proposed that a lot of these moons are big enough to actually differentiate like iron down to the bottom? Or are they not quite big enough, Tara?
They could, some of them could be. Like Europa and Enceladus definitely are big enough that there would be some differences in the structure on the interior. Like Earth has the iron inner core that's really solid, and then there's the liquidy outer core, and then there's the mantle on the top of that. We think that the same kind of thing probably would happen inside of these moons. To what degree it would happen, not really sure. It would depend again on how big that core is. If it's a very small core, much smaller than we might think it would be, then it might have a hard time doing that differentiation. But we do see differentiated bodies like that are really small. Some of the very small moons around Saturn and Jupiter. It's got all those little asteroid moons, and some of those can be big enough to be differentiated. So it's absolutely possible. We don't know for sure, though.
That's a great question.
Yeah, it's a great question. Let's see, another one here. Is there a lot of water on planets around other stars like planets here? Great question. And one that we can't really answer just yet. Because again, like we talked about with the exoplanets, they're really, really, really far away. So to us, they're very, very, very small. They're really hard to see. Now we're getting better at this. And in fact, this new telescope that's getting ready to launch, the James Webb Space Telescope, is going to be much better at this because it's going to allow us maybe not to see liquid water on the surface of a planet, but there's different techniques we could use like spectroscopy that allows us to detect water molecules, say, in an atmosphere of a planet. So that's something that we can do a little bit of now, and we're about to get a lot better with these new telescopes. So we'll be able to see water in that form for sure. We may be able to start detecting water on the surface of planets if it exists. So as far as we know, there's no reason why I would think that there wouldn't be just as much water elsewhere as there is on our planets here. Unless our solar system is just super weird, which we don't really know for sure if it is or not. But there's a good chance that there's just as much water elsewhere in the universe as there is here. Again, because hydrogen and oxygen are super abundant all across the universe. So we would think that there would be conditions in some way that would allow water to exist on these other planets too.
Yeah, I would say going back to, looking at this Crab Nebula, if you look at it, this multi-wavelength, and then if you just focus down just on really the hydrogen and oxygen, I think there's plenty of hydrogen and oxygen all throughout the universe, honestly. To think that there's probably many, many planets out there with, total oceans similar to ours, if not complete oceans.
That would be cool.
It also depends too on when we're kind of looking at these other planets too. Planets evolve over time and kind of change from you could be a total ocean world, and then you could become like maybe Earth, and then a couple of billion years could go by, and maybe you could look like Mars and have no water. So I think that's one of the things that people are going to have to figure out, kind of ways to, I don't know, kind of study that as well. Because if we're looking at, a planetary system, it kind of matters if we're looking at a planetary system like at the same time that Earth is, or same age as Earth, or one that's been around a lot longer, around an older star or something like that. So it's a lot of different variables there, but water's out there for sure.
For sure.
I would say it.
Yeah, sometimes when those planets are first forming, they're really, really hot. Because there's a whole lot of smashing things together and getting hit by little asteroids and stuff. So they may be too hot to have liquid water at the very beginning, but they may have water vapor, maybe like little atmospheres around them. So yeah, depending on the age of the planet, that can definitely have an effect.
Any other last questions here for water? Our first episode of our new mini-series.
Yeah, so like I said, next week we'll be talking about where all this water comes from and how it gets made and how it gets onto places like the Earth and all of these other places that we see it. The week after that, we'll be talking about missions that are going to look for all of this water. And then the week after that, we actually have a special guest speaker, Dr. Dave Brain. I don't know if you've seen him in any of our shows before. He's a professor here at CU. He does a lot of research on missions that go to Mars. And so he's going to tell us a lot about water on planets and in atmospheres especially. So that's going to be a whole lot of fun. He's always great to talk to. If no one has any other questions, then I guess we can call it a day. If you do think of any, go ahead and either drop them in that Google form and we'll get back to you. We may respond to you next week. You can also leave comments on the video here and we'll get back on those as well. And be sure, if you enjoy our videos and you like coming to Dome to Home, leave a comment and let us know. We love hearing from you guys about what you think, or if you have suggestions or comments. Definitely be able to share with your friends, send them the link, and let your friends and family know that Dome to Home is awesome. Be sure to check out our website too, colorado.edu/Fiske. There's all sorts of cool stuff you can do there, including look at all of our upcoming episodes. You can look at past episodes as well. There's also an option there where you can donate to Fiske and help us continue to run our virtual programming as long as we need to. We love bringing fun space content to you and would love to have a little bit of support from viewers like you. That's all I can think of. Jeremy, any other fine print we need to tell them?
I don't believe so. I think you covered it all, Tara.
All right.
I had a blast with everybody. Thanks for tuning in. And until next time, we'll see you. We'll see you next week.
See you next week, guys.
Have a great week, everybody. Take care.
Bye, y'all.